The floor is yours. Take it away.
Hello, everyone. Today I'm going to talk about graphene-based polarization-dependent terahertz photodetector. My name is Yuzhe Li, and the paper ID is A1004. Here's something about myself. I come from University of North Texas. My major is material science and engineering. And below is my contact information. So the presentation includes motivation, background, method, model, results, conclusion, and future work. So here's my motivation. Terahertz radiation is defined as radiation that has frequency between 0.3 terahertz and 10 terahertz. It's very useful in many fields like safety inspection and communication. However, there are still many difficulties in designing accurate equipment for generating and absorbing terahertz. In this presentation, I'm going to show a terahertz photodetector that has very good performances. So here's the background. There are many terahertz photodetectors, such as the heavily doped silicon and metal photodetectors. I choose to use graphene because it's cheaper, it's non-toxic, and it has simpler structure, which is easier to create in the manufacture process. Besides, graphene has zero band gap, low density, and the adjacent graphene sheets are bounded by van der Waals forces. So all these factors help to build a nice photodetector. Here's our theoretical considerations. So I use finite difference time domain software to simulate our models and solve Maxwell difference equations and problems of electromagnetic by using time domain method. I also consider polarization because it expands the information from light intensity and distinguish authenticity. Also, graphene's collective exciting terahertz surface plasmons, SPS. Those surface plasmon polaritons prove the existence of SPS in graphene. So here's my models. On the right of corner, you can see the actual shape of the cross graphene sheet, and below is the transmission performance of the photodetector. So I use FDTD to simulations that occupied a square area of 15 micrometers, and I set the light with the wavelengths of 50 to 1,000 micrometers shot from 25 micrometers above the graphene sheet. And the frequency domain power monitor was set at 75 micrometers, and below is the actual value of the length of our cross-shaped graphene. And to be mentioned, I also set the chemical potential at 0.5 microvolts and the conductivity scale at 2. And here's our results. So the polarization-dependent transmission can be represented by the first equation shows here. And from there, we can see when the polarization angle is 0 degree, the horizontal direction transmission determines the total value of transmission, while the vertical direction domains when the angle is 90 degrees. Different geometry of cross-shaped graphene can affect the performances of SPP. W0 is the resonance frequency expressed by the second equation, which is inversely proportional to resonance wavelengths. In the simulation, we set a non-symmetric model to refrain cancellation between two sheets and figure out the best size. So we also studied the two physical properties of graphene, which are chemical potential and conductivity scale. The equation of chemical potential is expressed here From the results on the right, we can see that the resonant wavelength reduces and the infrared transmission reduces leads to the rise of chemical potential and gets to a lowest point at 0.5 microvolts. The chemical potential is related to the carrier concentration that when chemical potential increases, more electrons can be included within transmission between intraband, and then the absorption of light increases. That leads to the increase of absorption intensity. The wavelength is also shifting from 124 micrometer to 75 micrometer. The number of graphene layer also matters. Increasing the number of graphene layer can increase the absorption intensity and the resonant frequency due to the SPP, cause strong interaction between two neighbor graphene sheets. The extinction of SPs requires higher energy from incident light that caused by dipole-dipole coupling. The transmission is the lowest where there are only two graphene layers. Transmission changes with polarization angles. Two transmission dips exciting in every transmission spectrum. So when polarization angle shifts from 0 degree to 90 degree, the transmission decreases to 126 micrometers in figure A. As conductivity scale increases, the lowest transmission point's X value decreases. The transmission curve declines gradually with the same X value for different peak value. The internal quantum efficiency, IQE, represents the efficiency of incident light absorption, which is correlated to incident light power, represents the equation of IQE. Photoresponsivity can be calculated out of IQE. When the polarization angle increases, the peak value also increases, and the wavelength value according to the peak is also moving right. Photoresponsivity can reach to 53 amperes per volts under 90 degree at a wavelength of 255 micrometer polarization and 35 amperes per volt under 0 degree polarization with 164 microvolts of wavelength. The electrical field is also simulated in FDTD, which measures the transmission of spectrum. Electric field distribution at the four sides of the cross-shaped graphene at both polarization angle of 0 degree and 90 degree. When the polarization angle is 0, the electric field is the strongest at the two width ends. Is the horizontal width and also the vertical width, which value goes up to 0.9 at the four corners and gradually reduces to 0.5 in the horizontal direction. When the polarization angle is 90 degrees, the electric field is strongest at the two length ends, which are also peaked at the four corners and then reduced going to the middle. And here's my conclusion. So the cross-shaped graphene has a good outcome. We can see that the transmission goes pretty close to 0. And the special nanostructure is applied due to LSP and the wide band gap of graphene. The photoresponsivity can reach up to 53 amperes per volts in 255 micrometer under 0 degree polarization. The relationship between size, chemical potential, conductivity scaling, polarization angle, and transmission are studied in this presentation. So here's our future work. So we plan to make actual crush-shaped graphene samples in the size that we find out is the most ideal. And we will apply experiments to prove the feasibility of the simulation theory. And here's our references. So here's all, and thank you all for listening.
Very nice. Very nice. And by the way, that was a very fine presentation. And you obviously are extremely diligent in very advanced scientific ways. So commendations for that. Now, you can nod your head because we're having trouble with the audio. Did I infer correctly from one of your early illustrations that what you're doing relates to those booths that we have to walk through at airports for security purposes?
Yes, that can be one of the application, but like, it's not. I say it's not the best because like what we have for like the security in the airport right now is, more than enough, and what we do are like, I can't say it can be used in the airport, but like, to like fully realize the applications, like. It's better to use it maybe in some communication, like telephone, and because like we have different frequencies, we use the terahertz frequencies, and that's like a totally different level for communication, and it can be used in our daily life or maybe some like military things. That would be pretty cool.
Okay. All right, let me ask a follow-up question. Can you give me an example in communications of what we are currently doing now and how it will be better if we implement the results of your research? And I'll mute myself for you to respond.
I would say, because right now it's only a simulation result, but I guess if it can be used like in the reality, like we can use terahertz to like, like when somewhere is not fully covered by AT&T, and by using terahertz because it's kind of like strong, and we can use it to like, maybe when you're going deep into a mountain, and we can create a foam by using terahertz, and it will be better to like communicate for them to like with the outside world, and like when they're being in trouble, and they can use that to like call for help.
Okay, I have one final question. How many more years, let's say you and your team were able to bring your research to market, and how many years from now would it take to turn what appears to be wonderfully theoretical into everyday use? How far away are we?
Okay, so like, I'm not sure if this is a very good simulations that can be like actually put into use, but it actually depends on like the fundings and like how many people that the group wanted to use in this project, because like in a lab we have several different projects and we kind of separating, and for our lab we mainly focused on simulation stuff, so we don't, and UNT doesn't like focus on the hands-on experiments in using the graphene. So if we want to like put it into reality, maybe like we need funding in build some hands-on experiment, or we need to like collaborate with another university.
All right, and I have one final question. under whose mentorship have you been working? Who is the PI of the lab that you are in currently?
I've been working in different labs. For this project, I worked with Dr. Xia. Yes, it's one of the professors from our department, but I've also been working, I'm more involved in Dr. Berman's lab right now because I'm kind of, she steals me from him. Yeah.
Okay, well then, what I would like to do is commend you, Dr. Berman, and Dr. Shah for their, first let me address them, for their championing research-based undergraduate education. And then I would like to commend you for obviously being a very astute and advanced student who is able to internalize and apply these very sophisticated concepts and concerns in the lab. And it strikes me that you're engaging in this kind of research has really put you years ahead of where an average undergraduate would be. So I commend your accomplishments and I commend their mentorship. And I would like to express appreciation to Paige Sanders for having been a marvelous host, and appreciation to all who have helped put together this wonderful Scholars Day where we could experience your learning and your research. So my appreciation to everybody.
Thank you so much.